so that's a little bit about the versions. So we're gonna talk about the stack next. So Android stack. Um, so any questions on this so far on versions? Everything makes sense? Yeah. Okay. So let's talk about the stack. What we've got going on here. So basically, you guys probably saw a picture that looks similar to this. This is essentially the high level what the entire Android operating system is like. Now, let's talk about each piece separately. And we're gonna, but just by the way, we're gonna sort of do it this way. So we're gonna go bottom up. So at the bottom of it all, we have the Linux kernel, right? So Android is built around Linux kernel. Now it's not Linux, it's Linux kernel, right? So a lot of people, think, oh, it's another flavor of Linux, possibly like Ubuntu is or something, or one of those. Basically, Android is built around the kernel itself. So that 1.5 megabyte file out of a couple of hundred megabytes that we have as part of the entire platform. So it's a very small piece of the whole puzzle. Now the question is, why Linux kernel? Why did they pick this as a sort of the basis? Any ideas?
Cost.
The cost, the price is good, right? The price is right. It's open source, yeah. Although I'll double click on that because open source means many things. Any other suggestions? So remember, one of the things that I pointed out was this vision, right? And we said we want to create a platform that's going to run on many different devices. So one thing that Linux is really good at is the driver model for Linux is pretty well understood. So we actually know how to port Linux to many different platforms, right? So that's a big benefit of Linux. That we can easily make it run on Qualcomm chipset or Intel chipset or MIPS chipset or different things like that. So that's a good thing. Secondly, Linux is very secure. So basically, it's an operating system that's been in very harsh environments over the years, and we know quite a bit about its security model. So that's a good thing as well for Android. And I know some of you are involved with the government work, so you're probably concerned about security to a certain extent. So that can actually, it has some really strong plumbing for being a very secure platform, Android. Although there's a lot of shortcomings today, but those are things that we would predict are going to be hashed out. Unlike for example, BlackBerry, which most enterprise folks would consider the gold standard for mobile security, BlackBerry trusts its security to Java, so it uses Java security model. Android doesn't. Android actually passes the security down to kernel. So it's Linux kernel that has the final say in terms of who can do what. And that actually is very significant because it allows us to do some really cool things in Android that are never going to be possible on BlackBerry, right? Up until the QNX version, right? So for example, you could not have native code as part of your BlackBerry app ever because that would break the Java security model. In Android, you can. So for example, if you want to create another Angry Birds game, right? You can do that physics calculation, that physics engine. You could do that in C++, and make it run really fast, right? And still make it part of your application, and still distribute it through the market, and still have everything be super secure, right? Yeah.
Super secure. Why Android has it? Device usually very hackable, right? Usually you get root access and everything. Right? So why is that?
So if it's also super secure, what's the why is it rootable and so forth? So the plumbing for Android is really good in terms of the how it's designed. There's some other shortcomings. One has to do with the fact that how the apps are distributed. So a couple of things that are sort of problems. One is the Android has the most malware, spyware, things like that, the bad stuff, right, out of any market, and that has to do with the lack of curation on part of the stores. So Google's Android market, for example, doesn't do any curation. So basically anything is allowed, even the really bad apps. Okay, that's a problem number one. Problem number two, with respect to routing and stuff, that's just because it's an open system. So a lot of other people are creating alternative versions of Android, like a bootleg versions of Android. So basically, you can buy a phone, but you can re-image it with another image that then gives you, for example, access. Yeah, so Kindle Fire is based on Android, but it's not a Android compatible device, right? So whatever it does is, it's kind of like it's just a modified version of Android altogether. And yeah, that's just how they designed it. So it really has to do, to root a device, you have to basically get read-write access to the system partition, which we'll talk about later on. And to do that, it's usually the bootloader that's the weak link. So getting the alternative bootloader, makes it easy. So, and certain companies like HTC, for example, they're now just providing that unlock. They're like, hey, you should be able to hack your phone if you want to. So it's just philosophical difference, right? Whereas other platforms like BlackBerry or iOS, where things are sort of like very vertically integrated, they just don't want you to shoot yourself in the foot, right? So that has a little bit to do with that. Mm-hmm.
So when you talk about the security as based on Linux security, that means is it like the groups and users, and we have to design our apps keeping that in mind?
So you do not need to worry about that too much as an app developer. You would care about this more as a platform developer. So basically, when it comes to Android, you guys can wear two hats, right? You can be an app developer developing apps. That's your final shippable is an app. You could be a platform developer. Your final shippable in that case is an Android system. It's like a modified Android system, like Cyanogen or something like that, right? Or I know Qualcomm does a lot of internal stuff. And actually, Qualcomm now is the gold standard for build systems. So it's not even Google anymore, but it's a lot of carriers now go directly to Qualcomm to build stuff, right? So got some stuff really down well. So yes, it is based on UIDs and GIDs, but no, you do not, as an app developer, you don't care about that too much. But back to Linux, like I said, it's not your standard Linux. So in standard Linux, you would expect to be able to create users, right? On Android, you can't do that. There's no etc password file, right? So user management is done dynamically. It's actually a C file that's compiled into the platform. It's kind of weird. You don't have fstab. You don't have your standard you don't have windowing toolkit. There's no X11. There's no even libc library technically. So there's a lot of things that are stripped out that you would expect in a typical Linux. So that's a little bit about Linux. Android trusts it, uses it a lot for things like networking, drivers, radio drivers, things of that nature. So on top of that, we have native libraries. Native libraries are basically things that came from the other, usually came from the other open source projects. So for example, you guys who did PhoneGap stuff, PhoneGap is based on WebKit, which is basically just an open source project. So we copy pasted it into Android platform. Media codecs, OpenGL, OpenSSL, all those sorts of things are copy pasted borrowed code. One sort of notable difference is Bionic. So for those of you who did C, C++, you may know that there's something called libc library, right? That's kind of like your core C library. Well, Android doesn't have it. It uses something called Bionic, which is basically a rewritten version of libc. Comes from BSD project and has to do with licensing. So that's a slight difference in terms of that. By the way, do you guys know much about open source and licensing in general? So this is the talk that I did on what it means to be open, and as part of that, I kind of broke down the open source licenses. Basically, you have about in open source world, you have hundreds of different licenses, right? There may be like a dozen that are more commonly used. But essentially, you can break them into two buckets in terms of what we care about. And it breaks down like this. I basically put it based on, does the derivative work fall under the same license or not, right? So that's the biggest question. If you derive some work, does that work have to be part of that license, or it could be something else? So if it's yes, that means that ultimately your code is going to fall under one of these major licenses, either LGPL or GPL, right? If it's no, okay, then your work is going to fall under one of these licenses: Apache, MIT, or BSD. Okay. So if you think about, if you go back to that vision that we had for Android, which is to basically have many have a mobile platform that runs on many different devices, that means you're going to have other companies work on this project as well, right? So that would basically mean that you would want companies like Qualcomm or HTC or Samsung or Motorola to be innovating on top of Android, having their engineers work on stuff. So for that to be feasible, presumably those companies want to retain the rights to the stuff that they do. So basically in Android, we try to do most of the things under this realm to be friendly to those entities, right? So that's sort of the goal in terms of licensing. And if you look at the entire stack, right? So the apps, most of them are open, Apache 2 license. So that's in terms of the apps that ship with Android. Framework is all open. It's also Apache 2 license. Now libraries are pretty much all open. Some have different licenses depending on if they come from other open source projects, but you usually don't derive work there, so it doesn't really matter. The most problematic is basically the bottom stack. And it's problematic because we have two extremes, right? On one extreme, we have overly open source license, which is like Linux, right? Which is GPL code. So anything that you do on top of Linux, you have to push back to the Linux community, right? You don't get to keep it. So it's overly open. On the other hand, we have proprietary stuff, like drivers, right? So for example, if I want to modify create an Android that runs on new Samsung phone, well, I'm likely not going to be able to get some pieces that are key pieces, like the drivers for radio, the drivers for GPS, the drivers for screen, etc., etc. That tends to be a proprietary code, never released, right? So that's sort of the part of the stack that's slightly problematic when it comes to licensing. So that's kind of good to know. That explains why we have Bionic. One of the main reasons is the licensing, to basically bypass the LGPL-ness of libc library. There's apparently it's kind of like a gray area. There's not a lot of lots of cases out there, but if you statically link against LGPL code, your code should also become LGPL code. So that doesn't work for Android very well. So that's why they kind of changed that. So that's a little bit about native libraries. Any questions on that, or it's all good? Cool. So one of the things that we have there is in that stack is something called Dalvik. And Dalvik is basically the replacement for the Java virtual machine. Okay. Now, most of you, does anybody not know what Java VM is? Most of you have some Java experiences, right? Okay, so you guys know what Java VM is. So why would they replace a Java virtual machine? What's wrong with the standard Java? Well, there are basically two things, two good reasons. One is the business reason, one is the technical reason. From the business standpoint, Java VM costs money. It's owned by Oracle. If you want to license it, you would have to go and line up around Oracle's building and, kind of have them take you to the cleaners, right, to get the licensing in place and so on. And so if that was the case, that would not work very well with the mission of Android to run on many different devices. And if everyone had to go to Oracle for licensing, that would not be very good for Android. So Dalvik is free as in Apache 2 license, so we don't have to worry about that. But more importantly, it's the technical differences. Okay, so Java Java was designed to be sort of one-size-fits-all VM. So you have it in tiny little BlackBerries, and then you have it in your supercomputers, right? Well, over the years, most of the optimization has actually been in the supercomputer realm, right? In your web servers, things like that. So it's been optimized for that. Now, when it comes to optimization, Java's been designed to work on mostly Intel-based computers, right? That's what you got in the data center. The problem with that is that Intel-based computers tend to be designed for devices that can have as much power as they want. So when it comes to mobile, one of the constraints that we have is the battery. It's actually the single biggest constraint. It's going to be the battery, right? So Intel chips tend to run warmer, use more energy than ARM-based chips. So Dalvic's been designed to run on registry-based chips as opposed to stack-based chips, so which tend to run cooler, right? That's why your phone doesn't heat up as much; it doesn't use as much battery. So that's one of the reasons why we have the how it's been optimized. Secondly, if you think about a standard computer, you guys may know this, but in Java, what happens is when you want to instantiate an object, right? What you do is or not you, but the virtual machine, goes to the file system, finds the class file, then loads it up into memory, right? And then it creates that object. Which makes sense because your hard disk is slow, right? Your hard disk is spinning at whatever, 5,700 RPM or so, right? So it's relatively a slow medium. And you want to load it up in RAM, which is much faster and you have a lot of it, right? The problem with mobile is that we don't have a hard disk, so there's nothing spinning in here, hopefully, right? So we have RAM and we have flash, and it's about the same speed, right? So and we don't have a lot of it, so there's no point in actually doing that copying, right? So Dalvik does some interesting things where it only copies on write when it actually changes stuff, right? So if you want to actually instantiate an object, you can just point to it on a disk and say, there it is. So it does some interesting things to cut down on memory consumption and so forth. So it's mostly battery and memory optimized for mobile devices. So that's what Dalvik is. A little bit of a trivia. The name Dalvik is named after this village in Iceland. It's actually a fisherman village in Iceland, and that's what it looks like. It's got a church. That's about it. And it's actually designed by, coincidentally, by my neighbor, Dan Bornstein. We are in the same 5-unit building in San Francisco. And so he worked for Google, and he built Dalvik from the start. He named it and everything. He's no longer there. And there's a little tribute to that. I got this license plate, but it's on Sasha's car. So if you see a little beat up Golf with Dalvik, that's our license plate. So just so you guys know. Yeah. And also Dalvik is the centerpiece of the lawsuit between Google and Oracle, which I'm sure you guys have heard about. So that's something that's going on. Yeah. So Google TV does run on Intel-based on x86 chips because we don't have a battery constraint, right? So these are devices that are plugged into a wall. So they've been working with Intel to basically port Android to Dalvik code to Intel. Dalvik is written in such a way that it's fairly straightforward to do a basic porting. So most of it is actually ANSI-C. So there's a version that you can just easily recompile, cross-compile for different architectures. So it's running on MIPS, it's running on Intel, it's running on ARM 5 and 7, and so on. There is a version that's then optimized. I think it mostly has to do with threading, how it works. So if you want to do kind of optimization, you can. But that's the main type of stuff that they do, optimization. If you just have a chipset, like I was involved in a MIPS project, just to get it going, it's relatively straightforward. But then the optimization is something you can keep on going for a while. So, yeah.
Compared to Java VM, what are the cons of Dalvik?
Compared to the Java VM, what are the cons of Dalvik? Well, for one, so Java VM is going to use more more memory. Let me show you a picture, and then we'll talk about that. So let me see where it is. Courseware, Android let me find a slide deck. Android internals. All right. So in standard Java, this is what you guys do. You write Java code, right? You compile it using Java C compiler. You get your class file, and then you run your class file on top of JVM, right? In Android, you do something very similar. You write the very same Java code. You compile it with the very same compiler. You run it. You get the very same class file. Then you recompile it once again with something called dex compiler. Okay, and then you get something called the .dex file. That's your Dalvik executable, right? So you put the Dalvik executable on top of Dalvik VM and you run it there. So these steps are sort of new. Now, keep in mind, when you guys do app development, you're not going to care about any of this because it just magically happens, right? But it's just more FYI. That's really what goes on behind the scenes. So a couple of things that are different. So for example, in Java, when you get this file, the class file, what you do is you collect all your class files into a jar, right? And then you apply zip to it, so you have a compressed jar. Well, so in Android, we don't do that because remember, we only do copy and write. In other words, we can do that thing where we just point to the file system to load a class, right? So that's why zip wouldn't work very well. So we keep this uncompressed. But even uncompressed bytecode, Dalvik code, is smaller than Java bytecode. Why is that? Well, Java is very verbose. So when Java compiles, you can actually decompile it and you get back like everything, including the class, everything except the comments, I think you get back, like all the variable names and all that, right? So Dalvik compiler, one of the things that it does is optimizes the code to be much smaller. So it essentially does obfuscation, but not intentionally. So it makes it much smaller. So that's why even uncompressed, it's smaller than compressed Java, right? So that's one thing. So that is much harder to go back to decompile it. So does that sort of make sense?
And when you publish your application, right, people usually hack your text file. Hack through the text file and can break your security and your like license check anything.
So can people break into your DEX file? To a certain extent, it's not as easy as Java, but yes, it's decompilable. So that's why since recently the Android tools introduced ProGuard, which is turned on by default. So basically, whenever you do a build, it's going to do a certain level of actual obfuscation of code, so that your code becomes less legible. Ultimately, everything is reverse engineerable, right? Like the question is how hard that is, right? You can take C code and decompile it. You just get gibberish, and it's really hard to assemble it back together. Java is really easy to assemble back together. So Dalvik is now making it harder, even harder with ProGuard. Yeah, I'll show you ProGuard tool when we get to the actual hello world. Yeah. So those are a couple of things with this. Now, what was interesting about this architecture, I was wondering, why didn't they just do this? I mean, why wasn't Java source code compiled directly down to Dalvik bytecode? Like, why do this extra step, right? Because this is really a disposable piece of code, right? Well, what I thought was really cool is that they basically took what Java compiler already does well, and then they built on top of that. So they didn't really reinvent the wheel. So this is relatively small. So that's a good thing. But what I thought was even cooler was that the fact that you can basically, you don't have to write Java code. You can write in anything else that compiles down to Java class file, Java binary code, right? So that's where Python via Jython and Ruby and things like that become very interesting, in Scala as well, right? So any VM-based code should run on Android, right? Which sounds great. Yeah.
So why is that some of the implementations are pretty slow? The word in the street is Scala implementations are 3x slower.
the Scala implementation is 3x slower. I'm not sure. I did not know that it's that slower. So I'm not 100% sure about that. So yeah. So you also one thing to keep in mind is what it means to be slow and where it is slow. So, for example, Dalvik did not have a just-in-time compiler for a very long time, right? Up until Froya, I believe. And I talked to their team, and I was like, well, how come, right? I mean, it's an old technology, right? Implementing a just-in-time compiler. Why not just hack something together and have it there? Wasn't it like sort of on a must-have list? They're like, actually, no. Most of the time, your app is just sitting there. It's actually not running, right? Like, if your standard application, right? You're just waiting for you to enter something, and you enter something and does something really quickly, and so on. So actual execution time doesn't really matter for most applications. Now, where it does matter are games, right? So games are sort of the actual code is the execution is important. So that's why you things that need to run really fast, you can do them in C++ via something called NDK, okay, Native Development Kit. So for example, your Angry Birds, you're gonna do the calculations, your physics engine in C++ and have it run really fast. Now Dalvik did get eventually just-in-time compiler, and it's based on and the code now runs 2 to 5 times faster. But that doesn't mean much. So, because most of the apps, you don't have a lot of code that actually runs. So, and then there's some really interesting ways how they implemented Dalvik just-in-time compiler. It's quite different than, for example, Java code and so forth. Like you guys heard of Hotspot, right? Hotspot engine. It's the Java just-in-time compiler. So things that Java does, it are optimized for code that is like, for example, a web server code, right? So in a web server code, you have, first of all, you have plenty of disk space. So Java, for example, uses something called a method-based just-in-time compiler. So basically, each method that you touch, like a function, then it converts to native code, the entire method, right? So that takes a lot of memory, right? But that's not a problem. I mean, hard drives are cheap, right? The other problem with that is that you need to run your code a while to actually get a substantial amount of it be converted to native. But that's fine on a web server. You just open up a web server, right? You have a bunch of people use your e-commerce app or whatever, and very quickly you ran it a lot of times, right? Well, on these things, it's quite a different experience, right? Imagine that I had an app that I downloaded and I need to use it many times before it actually gets substantial recompilation, right? So that doesn't fit on a tiny phone because I'm the only user. I don't have hundreds of users hitting my app. I'm the only user, so that doesn't work. And we don't have a ton of disk space, right? So Dalvik, for example, uses a totally different approach. It uses something called trace-based JIT. So those are some fundamental differences again between Java and Dalvik in terms of how they work. So cool. So that's a little bit about this. By the way, what I wanted to point out here also is that if you guys are Java developers, Android's Java is based on Java Standard Edition. So basically, you have everything you have in standard Java, right? So how do you do Android input output? Just same way as you do it in standard Java. How do you do threading? Same way you do it in standard Java. So a lot of these things are identical, right? The biggest difference what it's going to be from standard Java is that we yanked out anything that has to do with UI. So there's no AWT, there's no swing. Okay, and then we added a whole bunch of new things. But the point is, you have everything, almost everything that you have in standard Java, okay, plus more. Make sense? So, so back to this. So that plus more is usually this round here, application framework, right? So this is that, keep in mind, so far, this stuff here was mostly legacy stuff, right? I mean, some new stuff, I guess this was new, But a lot of these things are copy pasted from other code, and it's a lot of legacy projects and so forth. This stuff here is brand new, right? Purpose built for Android. So as part of that, we have the application framework. And application framework is basically exposing the capabilities of the platform to the apps. So remember that API level, 1, 2, 3 through 14, that essentially communicates what is possible here. So if we say this yellow line is at API level 14, that means I can expect certain pins, certain things that I can use that my app can run against. That's what that means. Okay, it's spelled out. There's an XML file that says at API level 14, these are the classes and these are the methods on it. Essentially the API. Okay.
You said that it supports the backward compatibility, right?
Mm-hmm.
But what about the APIs if deprecated? Then if you call the API, what happens on it?
Yeah, if it's a deprecated API, I mean, it's still going to be there. It's just that it's one of those, like, you should not be using it in the future. So when the API is deprecated, that usually means that there's a newer alternative to it. So your newer code should be using the newer alternative. The problem is that what if you did make a business decision that you are going to support the older code? So you find yourself in this interesting place where you actually have to use deprecated code. So Eclipse is going to keep giving you warnings, things like that. But you're like, look, I know I'm using deprecated code. I made a mindful decision to do so because I want to minimize the support that I'm projecting back is requires it.
Okay.
So as long as you know, but if you're say for example the minimum you're gonna go back is like 2.0, right, version of Android.
If the application is written in API version 10, for example,
Mm-hmm.
and then it's running on a device that has version 14.
Yeah.
And the APIs from version 10 was deprecated. You're saying version 14 framework still supports the old API.
Yes.
In a way.
Exactly. So it's not deprecated stuff is not gonna go away. It's just that so you're pretty much guaranteed it's gonna be there for a very, very long time, possibly indefinitely. But there's usually means there's a better alternative. So unless you have to support an older version, you should use the better alternative. Yeah. Mm-hmm. And sometimes, I mean, it's not the cleanest API in the world. Like sometimes they just kind of like don't like a certain class, and now because they have to support it for a long time, they can't really rip it apart and change it. So you're gonna find things like, for example, test case. For Java JUnit testing, there's test case, but then they didn't like it, so there's test case 2. So you have a lot of this like 2. Why 2? Because the one wasn't good enough. But they can't, because of the backwards compatibility, they can't just rip it apart.
So as an app developer, what is the expected life cycle of your app before you think you got to upgrade it to, let's say, the next version for the other? Is there a certain time?
As an app developer, what the expected length of time your app would
Before
be?
you have to basically hit your users with an upgrade of your system.
There isn't really there's no such metric per se. The only thing where time kind of matters is, it's actually on the next slide, is for the applications, apps must be signed, right? So you must sign your application, and actually most stores are going to ask you for a key that's good for 25 plus years, right? So, so that's sort of one of the best practices. When you sign your app, which I'll show you how to do later on, you should sign it with a key that's good for 25 plus years. And plus, you should sign all your apps from your organization with the same key, right? So, in other words, that key is really important. So if you lose it, you're in trouble, right? You're not going to be able to prove that the apps are yours. So yeah, so at the end of the day, we have apps. And so roughly what an application is, it's going to be some Dalvik code, some resources. So basically, resources are things that are not code, right? So your app is going to have some executable, but then your app also needs things that are not code. What kind of things do you have in an app that's not code? Icons, media, XML, strings, yeah. Those are all things that are not code. We'll talk about that quite a bit. Yeah. So that's That's another thing. And then you may, or this is optional, you may have some native libraries. Like in an Angry Birds app, you may have your physics engine written as a C code, right? So all that ends up being bundled in a file called APK. That's your final shippable. It's actually a zip file. You can unzip it and see all the moving parts inside of it. Yeah. So that's essentially what that is. So that's a little bit about the apps. Ultimately, apps you can distribute them. Once you write them, you can distribute them in many different ways. One of the main ways is to put it in a store. So you can sign up for example, Google Android Market, pay $25, and you can then go and put your app up there, and it's available right away.
So it's not free.
No, it's not free to sign up for Google, but you just pay $25 once, and you can have as many apps as you want, and you can, do all that stuff. So right from the get-go, Android was designed to be a ecosystem in which you don't have a single store, but you have many different stores, which is really cool, right? It's very unlike iOS with an App Store or BlackBerry World and so on. But in reality, in practice, you only have the Google market, right? Google's Android market. So that wasn't so good for the ecosystem. Up until recently, Amazon has been making some progress with their market. So it's actually, there's now a second big one. But what we're seeing is a whole bunch of small stores emerge, right? So I'm seeing this in the enterprise world a lot, right? Like, for example, Cisco has their tablet, the CS tablet. Well, they're not going to allow it just to go to market and download Angry Birds or some other malware, right? So what they want is they want to create sort of a highly curated enterprise-grade app market, right? So they would do something like that. So a lot of even smaller companies could do something like that internally. So we're seeing a lot of sort of boutique stores emerge. That's a cool thing. So you can do that. So those are the markets. Side loading is basically a process of taking that APK, this is that file, and somehow putting it into your device. It doesn't really matter, if you put it on a website, you email it to somebody, or you simply do it via USB cable, right? So you can just basically plug in the cable and push an app in. So that's called side loading. Or you can create your own app directory, basically your own application. So that's a little bit about the stack that we have at this point. So any questions about the stack, sort of the big picture, what the Android operating system looks like so far? Yeah.
So if you're going to develop a game, your suggestion is to do it in C instead of Java?
So if you're going to develop a game, do it in C or Java. What I'm seeing a lot of game developers do as much as possible in C. I went to some talks that, I mean, I think it's a majority of the code is written in C, like something like 90+%, right? So one reason for that is speed, but I think the other more pragmatic reason is that that's what they're familiar with. A lot of these game developers are more of a C type of developers anyhow. So, speed is sort of like, I would say, a second reason. Not in everything and not always is C gonna be faster. It has its advantages, for certain computational things and so on. Because remember, Dalvik does get compiled into native as well, so at some point the difference becomes really minimal. One thing we do, one of the exercises we do for NDK, for writing native apps, is we create this Fibonacci example. And what I like about Fibonacci is that it's super small little example, so it's a very small algorithm. It's exponential in terms of how quickly it goes, and it's recursive. So we actually implemented recursively first, and you actually get C code outperforming Java about 1 order of magnitude, so about 10 to 20 times faster. 10 to 20 times faster. But the reason is mostly the recursion. If you do it iteratively, so you can, any recursive algorithm could be written as a loop, right? So if you do it iteratively, it's actually sometimes even slower to do it in C, because there's a certain cost of doing the bridge, the JNI bridge, the bridge from Java to C and back. So for smaller jobs, it's more actually cost effective to just keep them in Java than to outsource them to C. Yeah. But Gingerbread brought into the mix something called native apps, native activity, which is basically a way to write most of your Android code in C or natively. And that's mainly to support gamers. So, yeah.
If you write C code, it's more portable as well. Because
If you write C code, it's more portable as well. You're right, and it's actually kind of funny because, I mean, Java was supposed to be that write once, run anywhere code, right? I mean, that was the whole selling point of Java, was that portability. And now we're back like 10, 15 years later, you know, you're writing brand new code in C, right? Well, why would you do that? One reason for C is, like I said, performance. That's usually the main reason. The second reason is going to be legacy code. Like you have some, you know, I worked with a company that wrote a DRM solution, and you know, they wrote it like over the last 10 years. So they have this big chunk of code that they just don't have time to rewrite in Java. So they just want to wrap it in, you know, JNI and expose it to Android. But the third reason, which I thought was funny, was the portability. And there's a company called MyLookout. You guys may use it. It's kind of like a virus protection on your phone. You know what I'm talking about? So it's a free app, and it's pretty popular for virus protection. It's actually a company here in the city. So their CTO actually spoke at SF Android, our local user group. And so they do all their brand new code in C for portability reasons. So, yeah, it's interesting. We're back at square one. So, any other questions on this so far? Okay, so with that, let's do this. So what we're going to talk about next is we're going to talk about the Hello World example.